So what we are trying to do is write down all these stress components on the surfaces at x plus delta x, y plus delta y, z plus delta z, and also x direction. Like what we have done for the momentum conservation, mass conservation, similar kind of thing we are going to do for momentum conservation. But to account the forces, what we require is stress components and suitable areas. So the first, what we are trying to do is in the x direction, let us locate it. So x direction, first you have to identify what are those stress components. So for that purpose, what I am trying to use is something like violet color I'm going to use. Okay. So can you see the purple color x directional force?
Yes, sir.
Sigma xx is a stress component, and that multiplied by that particular blue area gives me force acting on the surface. Similarly, let us look at another purple color. Can you see that?
Yes, sir.
Wonderful. And similarly, look at another purple color. All these things are acting in the x direction on three different surfaces. And three different surfaces are at x plus delta x, y plus delta y, and z plus delta z location. So what I have to do, like sigma xx acting at x plus delta x location multiplied by its surface area delta y delta z. This is on one side of the surface. Back side also there is a blue surface. So that blue surface sigma xx subjected at x location multiplied by delta y delta z. This is one of the component which is acting on the blue surfaces at x plus delta x location and x location. Is this step clear? The x directional one of the force what I have written. Clear, not clear? If this notation is clear, this is the right time to ask me.
Yes, sir. It's clear.
Is there a person to whom it is not clear? Great, if that is clear. Now, in the same x direction, now I'm going to erase this purple. Now let us look at one more in the x direction. The other one is this one, sigma yx at y plus delta y multiplied by the surface on which it is acting. This is the one. Normal to that surface is in y direction. So the surface area must be delta x multiplied by delta z minus bottom of that floor also red color kind of surface. So that kind of thing is sigma yx acting at y location multiplied by normal is in y direction. So the surface is delta x delta z. So these are the forces acting at two different levels. And what I am trying to calculate is what is acting across that element. And we have written sigma yx delta z minus sigma yx expanded at y delta x delta z is the force acting on the surfaces passing through the material. That difference is acting. Similarly, let us look at the other directional force, sigma zx. So sigma zx acting at z plus delta z multiplied by delta x delta y, because z is the normal direction, minus sigma zx multiplied by delta x delta y. This is the total surface force acting on this entire control volume via control surfaces in the x direction. Is there a person having difficulty to deduce or understand this mathematical notation of this x directional force? Don't be shy. I don't feel unhappy about it, and also don't worry about your friends what they will think about it if you are going to ask question. If you have doubt, this is the right time to ask me. I will be happy to re-explain if you want. Is there a person having difficulty? No. Okay, fine. If this is clear, now let us use our standard Taylor series approximation. So sigma xx at x plus delta x is sigma xx plus x multiplied by del sigma xx by del x delta x plus r that delta x square, because I don't want to write further more things. And such kind of procedure we have already seen called linear theory. Only linear terms we are going to retain. Higher order theories are 1950s kind of era. Well before that, 17th, 18th, 19th century kind of things, still linear things. Minus the other term sigma xx. This entire thing multiplied by your surface area delta y delta z. Now that first component we have written. Let us look at the second component. This one. Taylor series expansion is sigma yx at y plus del sigma yx by delta y multiplied by delta y plus r delta y square minus sigma yx at y multiplied by delta x delta z. That is this term. So second term also done carefully. Now let us look at third term. The third term is the surface stresses acting in the x direction on the surfaces z. Sigma zx at z plus delta z is sigma zx plus del sigma zx by del z minus sigma zx multiplied by del x del y. These are the force contribution what we are seeing in the entire x direction, because already stress components multiplied by surface areas, it goes forces, all these surface forces, if I am going to write it, because it's product, this one gone, this one gone, this one gone. What we are left over is this one, this one, this one, suitably multiplied by their areas. So go to next. So the total surface forces acting in the x direction are del sigma xx multiplied by delta x delta y delta z, del sigma yx by del y multiplied by delta x delta y delta z, del sigma zx by del z multiplied by delta x delta y delta z. This is the total surface force acting on the material. According to Newton's second law, that total surface force contribution supposed to give us mass multiplied by acceleration. The rate of change of momentum is supposed to give you. Rate of change of momentum means first identify momentum for the fluid particle. Rho multiplied by that infinitesimal element delta x, delta y, delta z tells you your tiniest mass multiplied by the velocity what the fluid particle really acquires it, u. So d by dt of rho u delta x delta y delta z equivalent to this surface force distribution. That is the thing what we are writing it in terms of a simplified form. The same thing I'm going to write, because delta x delta y delta z is arbitrary. Whether tiny thing I would like to really take 1 millimeter by 1 millimeter by 1 millimeter or 5 meters by 1 meter by 2 meters, it's up to me, independent of which x location, which y location, z location I'm going to pick it. So this delta x delta y delta z, what I will do is I will take it out common. So write d by dt rho u multiplied by delta x delta y delta z is equal to the gradient of surface stress distribution multiplied by your delta x, delta y, delta z, plus in case if it is experiencing any other body forces, those body force contribution also one should really write. So just to simplify that entire thing, what we are trying to do, cancel out, divide this entire forces by delta x, delta y, delta z. That is the one what we are writing as d by dt of rho u is equal to divergence of stress components plus sum of other external body forces per unit volume acting on the system. This is what we popularly call as the linear momentum conservation principle in x direction per unit volume. This is also we will shortly see as Navier-Stokes equation. If it would have been that simple, people must have solved these equations several times long ago. It looks like a bit difficult. That is the crux of the problem. Because surface stresses, writing it, modeling itself is a bit difficult thing. Whatever the simulations you use at computer levels, they are more like approximations to these equations. And this is one of the challenging problems. So it takes some time to understand. But what we have to really learn is, okay, the overall theme goes in this way. You write down the stress components on each surfaces, and that is the fundamental things instead of forces. When you really write down all these surface forces, suitably multiply with areas, you will get total forces acting on that. That's supposed to be equated to Newton's equation of motion to write down something like the principle of conservation of linear momentum. Especially for fluids, we write it per unit volume. Once we write that, if I would like to generalize that for different directions, maybe the different directions are x direction. Maybe I would like to write it for y direction. So u component, I have to replace it by v component. And surface stresses, what I have to really look at is in the direction of y direction forces, I would like to really look. So the direction of force always be the second script, y direction. And surface are different. So the first surface is x direction. Let me use some other color. X direction is first surface, y direction is second surface, z direction is third surface. So there is a rhythm in between surfaces. X, y, z are surface directions. Even x, y, z are surface direction. The second subscript is your force direction. X direction force you want to look at. X direction force for x directional velocity component. So there is a rhythm. In the similar way, y directional velocity, y directional force, you have a rhythm. And the net force is acting in the y direction. That is the way you will be in a position to generalize it. So let us look at third direction. Third direction, so W must be the component in the z direction. Is supposed to be counted in the z directional force, z, and surface forces on different planes, x plane, y plane, z plane. And the derivatives are also rhythmic, x direction, y direction, z direction, and z directional force. That is the way you actually remember the things, because it's maths. Either one has to derive it, or perhaps easy way to remember is in that way. Now you will see the advantage in looking at either Gibbs notation or indicial notation. The formulas looks very complicated and ugly. If I would like to really write it in Gibbs notation, very shorthand notation, this entire thing, I can write it d by dt of rho u bar, the vectorial quantity. This entire thing, divergence of your sigma. Sigma, you already know sigma xx, sigma yx, sigma zx, sigma xy, sigma yy, sigma zy, sigma xz, sigma yz, sigma zz. And what is acting on that? Del by del x, del by del y, del by del z. And you are going to condense it. So you have divergence del dot sigma. Stress second rank stress tensor, you are condensing it, gradient operator, so it becomes force terms. And here that force terms, what you are seeing, this is the x directional force, y directional force, z directional force, plus whatever the body forces per unit volume. If you remember, this is good enough to really write down that. You may not even have to remember, it naturally comes out when we are going to work out the problems. Great. So once that Gibbs notation is clear to us in terms of Newton's equation of motion or linear conservation of momentum, initial notation, if one would like to really write it, d by dt, u is a vector with I directional things, del dot sigma, so del j sigma ij, so jj condensation happens, I directional vectors you will be having, and summation f fi. That is the easiest way to really go ahead with this momentum conservation principle. Now at 1750, people have already derived such kind of force balance by extending from 16th century kind of Newton's equation of motion. Then they realized that, hey, it's okay to write abstract math like sigma, blah, blah, blah kind of thing. But what does it mean sigma? I cannot really find out that, especially for fluids, because I can apply forces. But for fluid, how will I even in a position to really find out something like this much extension happen? Is non-trivial task. So at that point of time, this Cauchy, the mathematical genius, Cauchy, Cauchy. Did you hear this name? Hello?
Yes, sir.
Where?
Yes, sir.
Where?
Sign maths. Sign maths.
So precisely, Cauchy is the main contributor, trying to say that all the time you are trying to say, but 17th century, what are you going to really measure? It's impossible task. Other than this abstract thought process really comes, carefully do the maths and model it, then you verify the experiment. It's more like, think of the situation. Before Newton also, people knew that things are falling down from top to bottom. There's no problem. People even try to sail. Maybe in 1490s, 14th century, 13th century, even Indians try to sail through oceans. That means if you are sailing, naturally you must be knowing how much coal you require or how much manpower you have to really put it to really drive it, so that you can really go with which velocity you have to go. This kind of thing in principle you know, but what all we don't know is mathematical quantification. Newton is the one who tried to quantify it. Aha, okay, it might be a fictitious story. Apple is falling down. There must be something like G, gravitational force acts. So I need to really quantify how G varies with space, or perhaps I should be in a position to really write the force with which experience is Ma equal to mg. That is the one what people don't know before Newton. People knew that in a very vague way, this acts, that acts, hand waving arguments. It looks like so complicated. Hand waving looks very easy, but you cannot quantify, you cannot develop the things further. That is the place where Newton jumped into it, started doing this kind of quantification. Then over the time, this Cauchy, Laplace, series of scientists jumped into that, start exploring furthermore and so on, so kind of thing, using quantification, especially through mass, then try to hypothesize the things through theory. Then people started testing it. Aha, okay, you quantify that. Let me test it. You quantify something like F is equal to ma. Now let me apply that. Let me do the experiment. Aha, okay, the ballistic really goes in that way. It matches. Ah, now I understood that very clearly. Otherwise, it will be more like hit and trial. You shoot a cannon with certain angle, it goes, falls at some other location. You shoot another cannon at another angle, you will have that. Is not at all generalized way of looking at the things. Maybe shooting cannons is easy. What is so big deal? But introducing calculus is so difficult task. But once you overcome that, because only these fundamental scientists does that, going through all that pain carefully, going quantifying those kind of things. Once that quantification happens, when you are going to learn that, you will be perplexed, really confused. What is this hell I'm doing? Why we are really bringing such kind of complication? Why can't we talk in a simple way? But that is the pain what they went through it, and we are appreciating that pain. Aha, okay, this kind of complexity you really went that. Now we are more like a very relaxed and privileged society to use such kind of theoretical framework, simplify to understanding. And that major step what Cauchy has taken. So what he did for the Cauchy and also series, because even though if I am saying some name, it's not absolutely truth and attributed to only that person. He might have overlooked at other giants and their shoulders, try to really see, learn it, go ahead and try to construct it. And that intricacy, what we are going to learn as called something named material constitutive equation. Modeling, you will call. Sigma, you are defining it wonderful, Raja. There is no problem. But the easiest thing for me to really realize is maybe whether it is a fluid material or a air balloon, or it can be piece of chalk, any kind of thing where it can really undergo deformation, breakup, and so on, so kind of thing. Can I really compress it equally in all directions? If that kind of force exists, we will call that one as pressure. Basically, the stress component, or usually people call that one as hydrostatic part. You take a material, it might be experiencing complicated stress strain, but equally normal to the surface, towards the surface, not away from the surface. Towards the surface, equally, can you really apply this kind of components? If that is the case, you call that one as hydrostatic pressure. The stress component, if you want to really write it like Pi minus Pi, that is minus P 1 0 0 0 1 0 0 0 1. Such kind of contribution, he has broken down this stress into one hydrostatic part where equal principal stresses act and unequal principal stresses act, call that one as deviatoric part. Why he is trying to split shortly, we will see. Such a kind of complicated state, I will be trying to break it down into hydrostatic part and deviatoric part. And the deviatoric part, I'm going to balance in terms of whatever deformation is happening inside the system as 2 mu multiplied by your strain rate tensor. So some material is getting stressed, some material is going deformed, and so on, so kind of thing. So each of these things experience different stresses in terms of whatever the components I'm trying to break it. I break it like hydrostatic and deviatoric part. And that deviatoric part, he tried to model it like 2 mu multiplied by Eij, especially for homogeneous isotropic Newtonian fluids. Newtonian means we already have seen shear stress proportional to shear strain rate. Isotropic means in all the direction the material properties will be one and the same. Homogeneous means the same material you will see. It is not a mixture. Even if you have mixture, you are attributing it to some density, conductivity, whatever that. The similar kind of properties, thermophysical properties, I should see it. For example, I have a pen in hand and the material, we don't know whether it is isotropic or not. That means if I stretch it in X direction, if I stretch it in the Y direction with equal kind of components, it should behave it in the similar way. Homogeneous, maybe if this plastic is completely made with a similar kind of material, same kind of material, the density at each and every level might be same. Even though this polymer is combination of different materials, but overall effect, I can always attribute to same density throughout. Because saying something like homogeneous is not obvious. Salt water, you take it. Salt is already dissolved. It's neither water, it's neither nor salt. It is a combination of that. More like you can think of mythological figure like Narsimha. It is neither man nor animal. Something more than that. In the same way, homogeneous material, if you are saying, having same kind of thermophysical properties may not be easy. It might be combination of different things, but you try to pretend that it is having same density. Such kind of approximations are very useful for mass. And if we are going to do for thermophysical properties, we call homogeneous. Based on space, you take any space, same kind of properties you are supposed to approximate. Immaterial of direction, if you are going to see that, you will call isotropic. Newtonian means shear stress proportional to shear strain rate. Under those approximation, he tried to simplify that. You can always write your shear stress component, the stress component as hydrostatic part plus deviatoric part. And this deviatoric part comes because of viscosity. Then the rest of the guys really jumped on to say that, aha, materials always have something like viscosity. Whether it is solid, liquid, gaseous, or whatever that, they possess viscosity. The only terminology is different. Sometimes we will call bulk modulus of elasticity. Sometimes we will call something else. Then at your mechanics of solids, you will learn something named Lami's coefficients. And those can be simplified to really show that viscosity can be modeled in that way. That kind of painful process, what Cauchy has done. And this entire procedure, more popularly known as generalized Hooke's law. Though Hooke's is not the one who tried to really construct it, Robert Hooke, where stress proportional to strain kind of thing. Here, stress proportional to your hydrostatic part plus your deviatoric part is called generalized Hooke's law. And if I have that stress modeling, I can always talk in terms of my hydrostatic pressures and viscous stresses. So divergence of sigma is divergence of minus pi plus mu multiplied by del u plus del u transpose. That if you simplify it further, some other day we will see that this entire thing can be written as minus grad p plus mu del square u. And that becomes the starting point of your Navier-Stokes equation. At this point, don't worry about each and every micro detail, but just have a generalized overall theme. You have finer size materials, surfaces, stresses are acting on that. Different surfaces, different stress component. If I carefully balance all these combination like summation, I will be going to write my Newton's second law of motion on the tiny element. D by dt of rho u is equal to divergence of stress plus external body forces, and that stress term somehow Cauchy jumped into the picture using these Lami's coefficients and so on, He tried to simplify into hydrostatic and deviatoric parts. Once these things are clear, one will be in a position to really write stress is equal to minus pi plus mu del u plus del u transpose, which one can write it like divergence of stress is equal to minus grad p plus mu del square u. We will take shortly 5 minutes break. Just give me 1 more minute to close it. After that, we will take 5 minutes break and we will catch up. Why I'm saying this is so complicated and also important in the industrial revolution development is even Archimedes know how to do hydrostatics. However, he doesn't quantify the things. It's more like empirical way. Somehow some magic eureka moment happened. You try to write that force, whatever it experiences, buoyancy forces, equal to how much volume displaced. You will be in a position to write it like a law. Law means usually you cannot prove it. You observe the things based on certain facts. You just write it. You propose it like a hypothesis. If it is so popular, very well tested, working, you will start calling it like law. If that hypothesis is failing certain places, you won't call it anymore law. Similarly, Newton's law, we are writing it. We don't know. We can test it. It is working. But from fundamental principle, trying to prove that the rate of change of momentum supposed to be equivalent to external forces is not that easy task. That's the reason we call Newton's equation of motion and is Newton's second law. You will apply. You know the structural form of the equation. You test it, whatever the object you take, application. It works very well. You start writing it, apply many engineering problems, you do technical advancements. But at one point of time, suddenly some stalwart comes, hey, your Newton's equation of motion or Newton laws are going to fail under certain circumstances. Till that point of time, the second-rated scientists always try to apply it, simplify the things, feel like, oh, this is very good for engineering, I really love it. But the first rate scientist really comes, show you when it is going to fail. That is the thing what Einstein has done. Till that time, people are very happy with classical mechanics, trying to apply for Newton's equation of motion. When this kind of first rated scientist really comes, jumps, shows that, sorry boss, that's not going to work. There are certain conditions where it is going to fail and that require corrections. Then new theories emerges, like theory of relativity, maybe special theory of relativity, and so on, so kind of thing. At that point of time, maybe after some 50 years, 60 years, people suddenly comes into picture, hey man, even your theory of relativity is not going to work, or is not going to really capture some of the things. We are going to come up with something named string theory. And that way, people really come up, the first rated scientists. I'm not demeaning anyone, but what I'm trying to say is, these things looks difficult to digest, understand, takes time. But when we go through carefully, step by step, and so on, so stuff, we will understand the importance of that in the history. After that, you start beginning applications. So after this lecture, what we are going to jump into do is, we step into the shoes of second-rated scientists, try to apply certain problems, pick it, how I can really apply these equations of motion for typical problems. That is the thing what we will do. So the same Newton's equation of motion, if I am going to apply it in 3 dimensions, minus del p plus mu del square u, you write it in such a complicated terminology. Remembering such kind of structure is not possible. The easiest thing is remembering the Gibbs notation or initial notation. The rate of change of momentum is equal to the gradient of pressure plus your viscous forces. This is what we call, because of viscosity, viscous forces. This is because of pressure. Now, if it is steady state, you will have hydrostatic balance. If it is unsteady state, you will have this hydrostatics with viscous terms and external forces. So any hydrostatic fluid statics becomes natural choice to simplify from this equation. So how these forms really look like, that different story. That is the step what we are going to really look at. Our linear momentum equation, if we are going to write it, d by dt of rho u is equal to minus del p plus mu del square u plus summation of these external forces. If I would like to expand this Lagrangian derivative, if I am going to expand it, del by del t u dot of del rho u. So u dot del rho u is del by del x rho u. U dot del rho u is v del by del y rho u plus u dot del rho u, which is w del by del z rho u. This is the first x directional momentum equation. If I am expanding, is equal to minus del p by del x plus mu del square u Laplacian u, del square u by del x square, del square u by del y square, del square u by del z square, and summation of external forces. The rhythm, again, here we can see because of this initial notation, del by del x, del by del x, del by del y, del by del y, del by del z, del by del z. And u, v, w, w. It is more like your u dot del term. Now, u dot del applied on rho u, rho u, rho u, rho v, rho v, rho v. So must be rho u. These terms are what we call non-linear terms in the Navier-Stokes equation. So if I am highlighting, this is a non-linear term in the x direction, non-linear term in the y direction, non-linear term in the z direction. Whenever you have products of velocities, we call that one as non-linear. And the simple structure, it looks like u dot del of rho u. And the first term is temporal terms. That is del by del t of rho u. So our entire d by dt of rho u is del by del t of rho u plus u dot del rho u. The first one is called temporal acceleration. The second one is called spatial acceleration. This entire term, what we call spatial acceleration. Why acceleration? Because this equation, what we are trying to write it is force per unit volume. So kg per meter cube multiplied by meter per second is always there. And per density also, if we are going to write it, it naturally gives me only acceleration terms. So without rho, we will call that as temporal acceleration and spatial acceleration terms. The other names for these nonlinear terms are advection term or convective term also. Material will be get transported by these spatial terms from one location to other location. At suitable times, we will really talk about that. And these viscous thing, what we call viscous terms. Viscous forces per unit volume. These are called inertial forces per unit volume. The nonlinear terms, spatial terms, temporal terms, these are the terms which are going to generate inertia in the material. You apply the forces on the body, it starts trying to change its location, is trying to change its velocity. Such kind of forces, what we call inertial forces. Maybe it is at rest. Because it possesses inertia, you have to apply forces to make it to move. So it's going to gain that. So you call that as inertial forces. And the other term, because of viscosity, what you are getting called viscous forces. Because of pressure gradient exists. Maybe there is an overhead tank, there is something like a pipeline. Because of this potential difference, like high pressure, low pressure kind of thing, flow try to pass in case if you open the valves and so on, from one location to other location, one pressure to other pressure also is start traveling, moving. So pressure gradient actually helps in terms of setting the objects into motion, especially fluid. Because of their combination, you are going to acquire inertia. And it's always the important question whether inertia force is large or viscous force is large. And people usually compare your inertia force to viscous force. That technically people call Reynolds number. That was done in 19th century. Any turbulent motion, wiggling, jiggling, chaotic kind of motion happen at your equation level, your inertia forces become so large compared to your viscous forces, naturally fluids start getting distorted. Maybe you have an incense stick, you are lighting, and there always be plumes which are wandering and so on. Compared to the viscous, which is trying to make it more like a smooth laminar kind of motions, your inertia forces are somehow triggered in so large such that it becomes turbulent kind of things. So whenever your inertia forces start dominating, the particle acquires huge amount of accelerations, velocities, move in a very complicated way. Now, can we okay, I have learned these kind of math equations, blah, blah, blah kind of stuff. Hi guys, I don't know why page has didn't change. Let me reshare it. Okay. Can you see the aerofoil?
Yes, sir. Yes, sir.
Wonderful.
Yes,
Okay,
sir.
Raja, we learned some math. We have reasonable grip in terms of notation and so on. Can we really apply it to certain specific problem so that I can really understand how to apply mass conservation and momentum conservation, calculate the forces and so on. That is the step where we are heading in terms of fluid dynamics. Whether it is a statics problem or dynamics problem, is just like suppressing some terms, keeping some terms and so on, so kind of stuff. Can I really apply that? That is the story what we are going to learn now. And especially that will be handled by two approaches. Whether you use pen paper or develop computational program, it will be depends on two approaches, namely called integral approach and differential approach. This is more like an algorithm what you are going to apply on any typical flow problem. It's more like algorithm. If you do those steps, you will end up with a careful way of looking at the problem and the numbers. That algorithm, what we are trying to look at. To learn that algorithm, whether it is integral approach or differential approach, we need to understand two concepts named control volume and control surface. For example, you are trying to look at aeroplane. And in the aeroplane also, I don't want to really look at that complete thing. Maybe it can be even drone, having a camera, flying. You took only one propeller blade, trying to understand the flow dynamics. And that in a pictorial way, what I have shown is there is some aerofoil. It's a 3-dimension. That's the reason I showed the ends as surfaces. Flow covering this aerofoil. Maybe I'm going to really look at Cartesian framework. So I have constructed some cuboid. over that aeroplane, or perhaps maybe on that wing, or perhaps on that propeller blade. Flow comes from one location, flow goes on to other location. That entire process I will be captured in a box, cuboid box. Flow comes in, flow goes out, flow goes out, flow comes in, and so on, so kind of stuff. Depends on the problem under consideration. Maybe if it is real aeroplane wing, which is attached to aeroplane, aeroplane is here. This is the wing. Flow comes from outside of that box, goes over that, swells, goes out. Maybe there might be some crosswise flow, might be trying to really come, moves, goes out. Maybe some crosswise flow also comes, takes turns and goes out. So your control box helps or perhaps permits any flow to come in, go out. Such kind of box, what we call control volume. And this box can be as arbitrary as possible. I can construct even a box only tackling aerofoil. That kind of complex box also I can really construct. But just for simplification, we are looking at rectangular parallelepiped. The surfaces means this surface or this surface or the other surfaces, what we are trying to say, those surfaces what we call as control surfaces. And conservation principle I will carefully apply within any fluid element. This is first thing. Within that box, whatever the fluid is there, we are going to write these equations for the fluid part. We are not going to handle structural part. The structural part you will learn at your applied mechanics. When structure is oscillating and so on, how it is communicating, on those things you will learn at your applied mechanics courses. But only fluid part, if we are going to look at, I'm going to apply conservation principle within this box. Wonderful. Now we begin with an example. Can you, okay, let us wait. I change the page. Hello. Okay.
Yes, sir.
Can you see the new page?
Yes, yes, sir. Yes, sir.
Wonderful. What we are going to do is, there is something like a T junction. Have you ever seen T junction in reality? T coupling. So this is the word what people use it. A very simple application. You will see this T coupling everywhere, wherever fluid machinery is there, whether it is rocket engines, whether it is ordinary pipelines, whatever that. Basically what you have is something like so your pipeline really comes here, connects there, again pipeline comes, goes there, you will be having your tap. Have you observed such kind of thing? Something like elbow.
Yes, sir. Yes, sir.
Elbow you must have seen. This is what you call elbow, where you connect your pipes, taps and other things. T junction is you don't want to disrupt the main line. Flow comes out of the system. This is what you call T coupling or T junction. Is there a asthma patient in our class? I mean, I don't want to reveal the name, but typically asthma patients sometimes who doesn't follow the nature kind of thing, but artificial kind of thing, they always use something named asthalin inhalers. The earlier days asthalin inhalers will be having such kind of shape, having canister here. You press this canister down, whatever the pharma particles really comes out, those pharma particles really come out like a jet, goes out, and finally it goes into the system. Shortly end of the class, I will show you how to simulate those kind of things. If you simulate, what will happen to these pharmaceutical particles? Such kind of things, these elbows and T junctions are quite common. And for that kind of application, what we are trying to say is, consider a steady flow through a water pipe joint, which is T junction. So the T junction perhaps looks like this. It can have even different kind of shapes. I'm just drawing abstract T junction. So one side of the thing is making 30 degrees angle. Other thing is vertically down. Other side is horizontal. Can you visualize this T joint? Fluid comes in one direction, fluid leaves, but it has something like a puncture or a hole. There is a leak happening. The T junction area at section 1 is 0.2 meter square, section 2 is 0.2 meter square, and section 3 area 0.15 meter square. And fluid enters at section 1 with velocity 5 meter per second. At section 2 velocity it leaves, we don't know. But at section 3 velocity with which it leaves is 12 meter per second. And there is a leak of 0.1 meter cube per second. This is the volumetric flow happening. Very simple problem. Without using these complex formulas also one can use. But once we have that mathematical formula, even complex problems we can so easily handle, because the algorithm works in that way. You don't develop a computer algorithm just to solve a plus b is equal to something like c. But once you learn that procedure, how complex might be the calculation, how many variables it might be, you will be in a position to generalize. In the same way, we are going to apply mass conservation principle for this T junction. Is the problem statement first of all clear? Or is there a person who don't understand even the problem statement? Fluid comes from one section, it goes to another section, we know something like leak. If that is the case, what will be the velocity with which liquid is going out of that section 2? Is the problem statement clear? Not clear? Hello?
Clear, sir.
Yes.
Great. Now can you calculate and tell me what will be the value? Okay, so for that purpose, what I am trying to teach you is, because we have identified something like control volume, control surfaces, the mass conservation principle, what we have learned from previous classes is del rho by del t plus del dot rho u is equal to 0 for a given control volume. This is the thing what I should apply. That means, though I have written for infinitesimal element, pile up such kind of infinitesimal elements each and every location, have those infinite elements, add them up throughout that entire box. That means mathematically, if I am saying that volume integral, control volume integral, del rho by del t dv of each infinitesimal thing plus volume integral divergence of rho u dv is equal to 0. This is the principle what we are going to apply. The infinitesimal thing, if I am going to pile it up for throughout that control volume, mathematically we will write it in this way, like volume integral del rho by del t dv plus volume integral del dot rho u dv is equal to 0. Because of Stokes theorem, the divergence term can always be rewritten in terms of surface integral. Throughout that control surface, the rho u dot nda of those surfaces gives me 0. Is this statement first of all clear before solving the problem? Hello?
Isn't it divergence theorem, sir?
Well, Gauss divergence theorem you can say, but I feel this is Stokes' second theorem. Stokes has first theorem and second theorem. First theorem is connected with your line integral. Second theorem is connected with divergence. It is quite popular as Gauss divergence theorem, I know, but I remember it is Stokes' second theorem. But I can confirm you whether the name is right or not. Is that fine?
Yes, sir.
Wonderful. But is there a problem in terms of applying theorem, volume integral into area integrals? Hello? Is this mass conservation at volume level, if I'm going to talk, is this step clear?
Yes, sir.
Hello? Wonderful. If that is clear, let us proceed. Just give me some time. Why I'm saying this is, it looks like a bit artificial why I need to really go through such a complex thing. But it is a generic principle. Even so many things are happening, coming in, going out, steady, unsteady, and so on. It will take care of it. So go to the next phase. So the first step, the principle, the integral analysis tells you first identify control volume, control surface for any problem, the generic description. So we know the material, something like a T junction, T pipeline. Identify control volume. That what I did with yellowish color. Wherever the yellow color I filled, the volume, three-dimensional volume is control volume. And it always be bounded by control surfaces. Maybe if it is a circular cut section, the cut section is basically the bluish one, this one, the surface. This is the surface. This is the surface. So just for simplicity, I have shown colors. The blue one is control surface, yellow one is control volume. And this angle is 30 degrees. Now, if I apply mass conservation at integral analysis, volume integral d rho by dt dv plus surface integral rho u dot nda is equal to 0, I have to apply. The first assumption what I am trying to make is, before solving any problem, flow comes from one location steadily, flow goes out steadily out of the system. That means all the time I will see same V1, same V3, same V2. I take camera, picture after picture after picture at the control surface is supposed to enter with V1, same, should not fluctuate with time. It should not fluctuate at V2, should not fluctuate at V3, should not fluctuate even at leak level. If that happens, we will call that process as steady state process. Under that steady state process, your del by del t of integral rho dv, which is commutative property, tends to be 0. This process, what we call steady state phenomena. So your del by del t of del rho by del t term turns out to be 0. Is this step clear? Now let us look at surface integral. All the control surfaces bounding the control volume, which are the ones? This is the one, this is the one, this is the one, and there is something like a pipe element, and there is something like this one, and there is something like this surface. So what I have to really do is, throughout these surfaces, calculate how much flux exchanges with the control volume. That is the meaning of this. The over throughout the control surfaces, calculate rho u dot nda. So expand that over each surface. So what I am going to do is, first I will identify surface 1, surface 2, surface 3, and this one surface 4. The surface 5 is the bounding surface of the material. Because this is rigid material, nothing goes out of this bounding surface what I am talking. So rho u dot NDA, by virtue U itself is 0, this entire term 0 on this surface, except CS1, CS2, CS3, CS4. On CS5, velocity is 0 because liquid is not coming out of the pipeline. So U component is 0, normal to that surface, that component is 0. So CS5 doesn't exist. Is that point also clear? Hello? Guys?
Yes, sir, it is clear.
Wonderful. So that means the complete control surface, surface on which S1 rho U dot NDA plus surface 2 rho U dot NDA plus surface 3 rho U dot NDA plus surface 4 rho U dot NDA. I need to calculate. Surface 5 already 0. Now let us evaluate on each of these surfaces. What will be that flux coming out from this system? So let us move on to the next page. Now, carefully look at what it means surfaces, because these steps becomes again important when you are going to learn computational fluid dynamics or advanced fluid dynamics and so on, so kind of step. Now, pick first surface. First surface is this. There are two terms like vectors, velocity vector and surface vector. Identify individually which direction these vectors are acting. Only focus on CS1. For any control volume in fluid mechanics, the normal vector always be opposite of that control volume. If this is the control volume, within that liquid is there, the surface wants to identify away from that surface, your normal vector acts. Away from it here, away from it in that direction, normal vector acts. So if that is the case, normal vector for this surface is, this is the one, normal. Velocity is, it is entering into the system in this direction. So U is in that direction. So on control surface CS1, U already I know, N I already know. Let us evaluate. So the evaluation is surface integral on CS1. Rho is rho, liquid water. U is, it is entering with a velocity V1 cos 30 I direction. So resolve U component in I direction as V1 cos 30 I and V1 sin 30 J, but in the negative direction. So V1 cos 30 I minus V1 sin 30 J. Dotting with normal vector is, this is the one. So normal vector, if I am going to show, black letter, N bar is in this direction. So if I am going to resolve, cos 30 minus cos 30 I plus sin 30 J. This is the normal vector to the surface, multiplied by the infinitesimal areas. That is the way I should write. Is this step first of all clear? Rho U dot NDA means, hello?
Yes, sir.
Yes.
Dotting with NDA. That means V1 cos 30 square. Right? Cos 30 is how much? Root 3 by 2 I minus V1 sin 30 is 1 by 2 J, dotting with minus cos 30 is minus root 3 by 2 I plus sin 30 1 by 2 J multiplied by DA. This is for the entire surface I would like to calculate. So rho multiplied by V1 3 by 4 I square minus 1 by 4 V1 J square multiplied by integral dA is the surface area of that element A1. Is that step also clear? How I have replaced the surface integral by one particular A1? Hello, guys.
Yes, sir, that's clear.
Why we are doing this is, let us think of a situation. My velocity is not uniform here. Velocity is not constant, but velocity here is function of x square y I plus y square z z. How will you be going to calculate anything like mass flow rate entering in the system? Mass conservation principle, how you will do? Something like our blood, arteries, veins, heart, this kind of things have very complex kind of structure. It's not necessary that all the time you will have same kind of shape. Sometimes it might be expanding, sometimes it might be collapsing. How are you going to apply your mass conservation principle? So there should be a generic thing. And that generic thing, what we are trying to learn for simple problem. So that simple problem, what we have looked at is a uniform velocity comes throughout. Cross-sectional area is uniform. It's not fluctuating and so on. So much simplification we have done. If not, this is the generic procedure, what we have to do, which is pretty straightforward. So now the total surface flux, what it is coming is minus rho V1 A1. Minus 3 by 4 minus 1 by 4 is minus 4 by 4 V1. So minus rho V1 A1 is the flux what actually comes into picture. If cut section is varying, maybe velocity is highly fluctuating, sometimes it is depends on space, you will never be in a position to get it unless you simplify that integral. That is the point of this integral analysis. Now let us look at the other surface. Similarly, second surface, rho u dot NDA on surface 2 is this. What is u component? U is going down. So 0I minus V2J. Starting with normal direction is in the same direction here. 0I minus J dot dA. That means throughout the surface rho 0I square plus V2J square multiplied by dA. So rho V2A2. This is the flux, what it is coming out from the surface 2. Is this step clear? Is there a person not clear? The surface flux, what it is coming out from the surface 2? Try to show that this is rho V2A2. Is there a person not clear? Hello? Guys.
Clear.
If it, okay.
Sir, clear, sir.
Wonderful. So let us look at the third surface. Again, same principle, surface integral rho u dot NDA. Surface is going in the horizontal direction. Normal is in the I direction. So normal is I plus 0j. Velocity is also in the I direction. So V3I j. So rho V3A3 is the surface flux which is going from the surface 3. Surface force 4 rho u dot NDA is rho multiplied by how much volumetric flow rate it is leaking. So rho multiplied by that volumetric flow rate. That's the way for surface 4 we will calculate. Now already we have calculated all these surfaces. So all the surfaces rho u dot NDA is surface integral rho u dot NDA plus surface integral rho u dot NDA plus surface 3 contribution, surface 4 contribution supposed to be 0. That means minus rho V1A1 plus rho V2A2 plus rho V3A3 plus rho into volumetric flow rate what it is leaking out is equal to 0. So minus V1A1 plus V2A2 plus V3A3 plus 0.1 is equal to 0. So naturally sign also taken care into the system. Any fluxes which are going out are positive naturally formed, because you can think this V3A3 is going out, V2A2 is going out. So whether it is plus or minus, naturally taken care by this vectorial notation. And whatever it is coming in is negative, that is also naturally taken care into the system. A generic version we have developed. So rho is constant throughout the system. So rho cancelled out. Minus 5.2 plus V2 multiplied by 0.2 plus 12 multiplied by 0.15 plus 0.1 is equal to 0. You simplify it, you will get V2 is equal to minus 4.5 meter per second. This is the way the liquid velocity which is coming out of the system. Is that clear, guys? Hello?
Yes.
Wonderful. This is the generic way you apply mass conservation principle. How about having a short examination right now? Not for grading, but in general, just to see that whether it is going or not in a careful way. So we have something like an air balloon. Think of a tank, more precisely a tank. A tank of 0.05 meter cube volume. It contains air. Maybe your cycle wala, whoever so filled already his tank, not pumping kind of thing. Already there is a tank, there is a tube. And when you press that cycle tube kind of thing, air really leaks into your cycle tire. So that means there is some amount of air which is already highly pressurized in the tank, comes out, fills your cycle tube. That means some amount of mass reduced out of that tank. If that is the case, can I really calculate how much amount of mass reduced out of the tank per unit time? That is the example what I would like to really consider. A tank of 0.05 meter cube volume contains air at 800 kilopascals absolute, and it might be at 15 degrees Celsius. It might be in a cold country, you can think of it. At time t is equal to 0, air begins escaping from the tank through a wall with a flow area of 65 millimeters square. You can always think of your cycle wala tank is this one, and there is something like a tube. That tube really comes very narrow thing. There is something like a hole kind of stuff with a pin. And perhaps if you are running your compressor, air continuously comes out of it. Maybe whole point of this tank is to store air at higher pressure so that you have cut off the line, but still air is highly pressurized. Whoever so comes with their bicycle, they try to really plug this one so that air fills in that cycle tire. You can think of that situation. That is the one what we are trying to talk about. A tank of 0.05 meter cube volume contains air at 800 kilopascals and 15 degrees Celsius. At time t is equal to 0, air begins escaping from the tank through a wall with a flow area of 65 millimeters square. The air passing through the wall has a speed of 300 meter per second. It gushes. When you press that pin, it gushes with such high speeds like 300 meter per second. Air might be compressible also, we don't know. And density of air is 6 kg per meter cube, maybe when it is within the chamber. Or maybe when air is leaking out, the compressed air which is coming out at 300 meter per second is 6 kg per meter cube. That can also be possible. Shortly we will see. If that is the case, because it is passing through the flow wall, 65 millimeter square at 300 meter per second, and density is 6 kg per meter cube. If that is the case, can you find out instantaneous rate of change of density? d rho by dt, can you really figure it out? Del rho by del t, because you are going to look at control volume. Can you find out what might be that? Can you tell me, using your +2 kind of Darcy theorem, try to figure it out what might be the rate of change of density within this system? This is the exam
Sir,
what I am giving you. Yeah.
sir, is it minus 2.34 kg per meter
Wow,
cube?
man. How did you solve it?
Sir, the mass flux out of the system is equal
Okay.
will be equal to negative of the rate of change of density times the total volume.
How did you know that? Is just by obvious or something like no, something is leaking, so naturally there should be a plus sign, there should be a minus sign, so on, so kind of combination?
Yes, sir. I mean, the mass
Okay,
that is
fine.
going out.
Wonderful. Great. That is the answer you will find, minus 2.34 kg meter cube per second. Now the question, systematically, if I want to do that, now how much momentum flux it is leaking out? Can you tell me? Hello? How much momentum flux it is going out? And now I'm going to complicate the problem. It's not just one tube. It has one area here, another area reduced and went ahead, and another area. This is also leaking, this is also leaking, this is also leaking. And perhaps it really turned out to sinusoidal kind of thing in this way also. The tube is such a fancy thing and air is leaking. Now, what kind of oscillations it is going to do in terms of this leak? Let us think of, I'm going to close. I'm asking different questions. Something like these tubes are closed. And it is very flexible thing. And some air is leaking and it is not fixed at this location. Now, because air is leaking like a snake, it is start doing to and fro motions. Whenever air leaks, it just start oscillating. What will be that oscillation frequency? I'm going to ask. How are you going to calculate? Hello? How do you apply? Or from previous knowledge? Does that depends on elasticity of the tube or not? Does that depends on cross-sectional area of the tube or not? Does that depends on outside atmospheric pressure or not? Even does that depends on temperature of the system or not? If you can really find out solution for that, I will get you one more Cadbury chocolate, what is that? Dairy milk chocolate. What I would like to have, there is a tube, the same problem, air is leaking out of the tube. Based on elastic properties of the tube, can you really figure it out what kind of snaky oscillations it is going to do? Quantitatively, not experimentally. How do you solve that? Hello? Based on the initial configuration, can you really figure it out? Hey Raja, maybe if it is right tube, when I derive it, this is the way it oscillates. Maybe you already given me something like initial condition. It is turned in this way. Air is trying to leak. What will be the direction of that oscillation? Maybe it is just a simple plain air balloon. I know that initial configuration. Based on the elasticity of the balloon, can I really predict what is that snaky kind of motion the balloon is going to have? Not a rectilinear thing, because of this continuous change which is interacting. How I am going to find it? That is the place where complexity really comes into picture. Our simplification won't come so easily. You have to really integral analysis use it. So shall I apply that for this simple problem to show it? Can I have 5 more minutes? Hello?
Yes, sir.
Yes,
Yes,
Any
sir.
question? Okay, if no question, let us first begin with a simple problem. The generic problems, we will look at it later on. This is the tank volume. It might be rectangle, it might be cubic, it might be triangular, pyramid, whatever. First, I'm going to identify something like control volume. So this is the control volume. The dashed lines I'm going to really show. Again, this is abstract. Whether it is spherical, whether cuboid, or it doesn't matter. Something like control volume I'm going to really identify. So I will call that one as CV, where our dashed lines are there. Control surfaces also I'm going to identify. That control surfaces I'm going to show blue color. This is CS1. And perhaps this entire rigid one is CS2, control surface. Now, my mass conservation principle tells me, begin Raja, del rho by del T plus your divergence of rho U is equal to 0. Write it at volumetric level, del rho by del T dV plus volume integral divergence of rho U dV is equal to 0 on the control volume. So on volume integral, del rho by del T dt dV plus, because of your Stokes theorem or divergence in Gauss divergence theorem, surface integral del goes of rho U dot NdA I have to really tackle. That means volume integral rho dV del by, okay, let me write it more carefully. Commutative property del by del T of volume integral on that control volume rho dV plus surface 1 rho U dot NdA plus surface integral CS2 rho U dot NdA is equal to 0. Surface 2, is there any air leaking out of the system? Because it is a closed boundary, U by definition 0. So this one turns out to be 0, the volume integral. Because U is 0 everywhere. Throughout that surface, I am going to integrate, everything is 0. If there is a puncture there, naturally, I will be going to account only that particular surface. Oh, I'm sorry, I erased something. The other surface, let us look at that one. The other surface is this one. Zoom in. So the surface is this one. The velocity is in this direction. The normal also in the same direction. So this one 0. This surface integral rho U is in the I direction. I plus 0j plus 0k dotting with NdA. N is also in the I direction. So I plus 0j multiplied by dA throughout the surface. If it is a circular surface, naturally pi r square area I will be going to do. Whatever might be, it is rho U A of that particular surface. This is plus del by del T of my volume integral of rho dV in the control volume. This entire thing supposed to be 0. That indicates that this supposed to be brought to this side with minus sign. Naturally, the minus sign comes into picture. So what is the velocity with which it is going out? 300 meter per second. What is the density? 6 kg. What is the cross section area? 65 by 1000 millimeter per second square, right? So millimeter means 10 power minus 3 whole square, 10 power minus 6. If you simplify this one minus, it turns out to be minus 2.34 kg per meter cube per second. This is the rate of change of interpretation, the rate of change of the mass of that air inside the system. That is the way it is going to change. Is that fine, guys?